Welcome. Today we delve into the more advanced realms of machine learning. In this module titled Advancing in Machine Learning, we're going to explore two critical and sophisticated techniques: feature engineering and hyperparameter tuning. These techniques are pivotal in enhancing the performance and accuracy of our machine learning models. As we journey deeper into the intricacies of machine learning, it's essential to build upon the foundation we've established in our previous modules. In the earlier segments, we've covered the basics of AI and machine learning, including understanding different types of learning methods and getting hands-on with building basic models. Now we're ready to take a step further and unlock even more potential from our machine learning endeavors. Feature engineering and hyperparameter tuning are the tools that can transform a good model into a great one. They are the fine-tuning mechanisms that allow us to extract more accuracy and efficacy from our data and algorithms. In this module, we will not only explain these concepts, but also demonstrate how to apply them practically. Our goal is to equip you with the skills to enhance your machine learning projects, making your models more powerful, efficient, and effective. Let's go into feature engineering. In this section, we're going to delve into one of the most impactful aspects of machine learning: feature engineering. But what exactly is feature engineering? Simply put, it's the process of using domain knowledge to extract features, characteristics, properties, attributes from raw data. These features become the input variables that feed into our machine learning models. The importance of feature engineering cannot be overstated. It's a critical step that can dramatically improve the performance of machine learning models. Effective feature engineering can mean the difference between a mediocre model and a highly efficient one. By carefully selecting and transforming the input data, we can enhance the learning process, leading to more accurate predictions and insights. Techniques in feature engineering. Data transformation. One of the first steps in feature engineering is data transformation. This involves modifying raw data to enhance a model's understanding of it. Techniques like normalization or scaling are commonly used. Normalization adjusts the scale of your data, bringing every feature to a similar range. This is particularly useful in models where distance measurements are important, as it ensures one feature doesn't dominate the others due to its scale. Scaling, similarly, involves adjusting the range of features, but it can take different forms depending on the specific method used, like min-max scaling or z-score standardization. Feature creation. Another pivotal aspect of feature engineering is feature creation. This involves creating new features from existing data. A classic example is combining date fields to create a new feature like duration, or breaking down a date into day, month, and year components. These new features can often uncover relationships in the data that were not apparent before and can provide additional insights to the model. Dimensionality. Reduction. Finally, we come to dimensionality reduction. This technique is crucial in dealing with datasets that have a large numbers of features. Techniques like principal component analysis, PCA, are used to reduce the number of features, focusing on those that are the most important. PCA, for instance, transforms the original features into a new set of features, the principal components, which are a linear combination of the original features. These new components capture the most variance in the data with fewer features, making the model more efficient and often more effective. Understanding hyperparameters. As we delve into another crucial aspect of advancing in machine learning, we focus on hyperparameter tuning. But first, let's clarify what we mean by hyperparameters. Hyperparameters are the settings or configurations that govern the overall behavior of a machine learning model. These are not to be confused with model parameters, which are what the model learns during training, such as weights in a neural network. Hyperparameters are set prior to the learning process and can significantly influence the performance of the model. The importance of hyperparameter tuning in the machine learning process cannot be understated. Choosing the right set of hyperparameters can dramatically improve the performance of a model. It's akin to fine-tuning an instrument before a concert. The right adjustments can make all the difference in the quality of the output. Tuning techniques. Grid search. The grid search method is one of the most straightforward techniques for hyperparameter tuning. It involves defining a grid of hyperparameters and systematically working through multiple combinations, evaluating each one. The goal is to find the combination that yields the best performance in terms of model accuracy or another metric. For instance, when tuning a support vector machine, you might vary parameters like the kernel type C, regularization parameter, and gamma, and evaluate each combination using cross-validation. Random search. An alternative to grid search is random search. This method randomly samples hyperparameter combinations from a defined search space. The advantage of random search over grid search is that it doesn't try every possible combination, which can be computationally expensive, but rather samples a subset of combinations, which can be more efficient, especially when dealing with a large number of hyperparameters. Automated hyperparameter tuning. Lastly, there are more advanced methods like Bayesian optimization, which takes a probabilistic approach to hyperparameter tuning. Bayesian optimization builds a probabilistic model of the function mapping from hyperparameters to the target evaluation metric and uses it to select the most promising hyperparameters to evaluate in the true objective function. This method can be more efficient than both grid and random search, especially in scenarios with a large number of hyperparameters and complex search spaces. As we wrap up this module on advancing in machine learning, let's take a moment to reflect on the significant concepts we've explored. We started with feature engineering, understanding its crucial role in preparing and enhancing our data for better model performance. Through techniques like data transformation, feature creation, and dimensionality reduction, we've seen how raw data can be transformed into a more informative and efficient format for our models. Then we ventured into the world of hyperparameter tuning, distinguishing between hyperparameters and model parameters, and emphasizing the pivotal role that tuning plays in optimizing our machine learning models. We explored various techniques from the methodical approach of grid search to the more randomized approach of random search, and even touched upon the sophisticated methods of automated hyperparameter tuning, like Bayesian optimization. Each of these techniques, whether in feature engineering or hyperparameter tuning, serves to refine and enhance the capabilities of our machine learning models. They are the tools that allow us to delve deeper into the nuances of AI, pushing the boundaries of what our models can achieve and ensuring that they perform at their best. As you continue on your journey in machine learning, remember that these advanced techniques are not just theoretical concepts, but practical tools that can significantly improve the quality of your models. We encourage you to experiment with these methods, apply them to your projects, and witness firsthand the improvements they can bring.